We have seen in the previous video examples of some ordinary differential equations and even an integral differential equation which arise in RLC circuits. And it's time that we'll learn about a very helpful tool which we can use to analyze such systems. So Laplace transform is this tool which can be used to analyze and design linear systems. Examples of such systems are electric circuits and other systems in engineering and science. And why is it helpful? Because it allows you to convert a rather complex and often unpleasant ordinary differential equation or integral differential equation into a simpler form, which is easy to solve. And this is the first step. The second step is to solve this algebraic equation, which is again simpler to do than an original differential equation. And the final step is to go back and to translate our answer to the language which we had originally, in terms of functions and unknowns and so on. So this is a three-step process, and we'll come to that much later in this course unit in more detail, but just bear in mind that the ultimate goal is to find a way to solve difficult problems easier than otherwise possible. So it is in effect a language, and as you learn more languages you become more flexible and able to solve and understand more difficult problems. Let's start from definition. But before we go to that, let's actually find out who is Laplace. So here you see a picture of Marquis Pierre-Simon de Laplace, who was a prominent mathematician, engineer, scientist, who contributed to pretty much every area of modern science and engineering you can think of. So you'll see his name appearing in multiple places. So don't be surprised, it's the same Laplace. So he was French Newton, so to say. And he even ended up in politics at some point because he was examining no less than Napoleon Bonaparte himself. But he didn't work as well in politics, unfortunately, as in science and engineering, and he was fired by Napoleon because he actually made more trouble in administration than he helped. And Napoleon told about him that he brought in the spirit of infinitesimals into administration. So sometimes science is not always the best administrators, but still he's a brilliant scientist and engineer. So what actually one of his creation? It's a Laplace transform. On the face of it, it's an integral. So if you have a function and you want to convert it into something else, what you can do, you can take this function and integrate it with the exponential function, and the result will be something else. So what do you think the result will be? Well, probably in your mind you will say it's another function, and it is right. So this is another function which depends on the variable s, because we integrate with respect to t. So, and we call it f bar often, with over bar above f. So that's just another function. So we take one function and then we go to another function. That's what Laplace transform is. So the important thing to remember that when you take Laplace transform of function which depends, say, on t, the result should not depend on t. It should depend on s. That's important because it's a common mistake in the solving the problems. If you take a Laplace transform, the result should not depend on the original variable, it should depend on a new variable. So if you take f of t and apply a Laplace transform to it, the resulting function will be a function of a different variable. That's important to bear in mind. And as I said, the most common notation is f over bar s, but you can sometimes use capital F if you prefer. But for majority of this course, this is what we'll be using. That's the main notation for Laplace transform.